All right, in this video, I'm going to overview the background sections of Lab 3. There are two of these. The first is on the Galilean Revolution, the four major discoveries Galileo made in 1609. And the second is on the nature of orbits, in Kepler's third law in particular. So let's open up the first of these first, on the Galilean Revolution. So in 1609, Galileo took a telescope. He did not invent the telescope, but he took a telescope and for the first time ever pointed it at the heavens. He looked at the four brightest objects in the sky, the moon, the sun, Jupiter, and Venus, and with each one, he made a revolutionary discovery, challenging the beliefs that were held at that time and the teachings of the church, the Catholic Church, at that time. Now, with the moon and the sun, what he discovered did not directly challenge the geocentric model, but it did contradict what the church had been teaching about these objects, part and parcel with the geocentric model, which they had adopted as truth. So what they were teaching, and this goes all the way back to Aristotle, who introduced the idea of circles and circular motion as being ideal or perfect shapes and motions. The church had been teaching that the moon and the sun were perfect objects, and by that they meant perfectly smooth, spherical objects, and in the case of the sun, unblemished. If you look at the moon, you can see it's blemished. There are dark regions and there are light regions, but they were teaching that it was perfectly smooth, and in the case of the sun, perfectly smooth and without blemishes. So when Galileo pointed his telescope at the moon, and you can do this yourself with just simple binoculars and confirm what he found, the moon is not perfectly smooth. It has craters and mountains and ridges, and these are very easy to see. In the case of the sun, he saw spots. Now, if I were to point a telescope at the sun and look through it, I'm sure I'd see spots too, but he kept very careful records, and what he drew matches up with what we now know to be sunspots. The sun is indeed blemished, and the moon is not perfectly smooth. So these two discoveries contradicted church teachings of the day, but not, as I said, directly test the geocentric model. Now, Galileo's most famous discovery is the moons of Jupiter. He discovered 4 new worlds for the first time ever, 4 new objects up there in the sky, other than stray comets and supernova explosions and things of that nature. And he watched these. You can see his original drawings here. They were in a line about Jupiter and moving about that planet. And this was a big problem for the geocentric model, because the geocentric model teaches that everything must go around Earth, Earth being the most important, all-important object in the universe. The heliocentric model, which says the planets go around the sun, doesn't have that restriction. You can have moons going around the planet, such as Earth's moon going around Earth and Earth going around the sun in the heliocentric model. But in the geocentric model, everything must orbit the Earth, and here he found 4 objects not orbiting the Earth, but clearly orbiting Jupiter. So this contradicted the geocentric model, but it's not really a strong test of the heliocentric model. You get that with the phases of Venus, and this is lesser known, but more important. This is a very direct, detailed, quantitative test of the geocentric and heliocentric models. In particular, each of these models make very different predictions for what phases Venus will go through as it goes around its orbit, and its angular diameter, how big it appears as it's going through these phases. So here you can see the data. This is the full range of phases and angular diameters that Venus goes through. But let's see what the two models predict. Now, with the geocentric model, Earth is, of course, at the center. Planets ride on little circles called epicycles, and epicycles ride on larger circles called deferents, and those deferents are centered on or near the Earth. Now, in the case of Venus, its epicycle, the center of its epicycle, is always on a line between the Earth and the Sun. So in this figure, you can see all the different positions Venus can be in with respect to us and with respect to the Sun in the geocentric model. When it's here, it's between the Sun and us, so its phase is new, and since it's close to us, its size is large. Then as it works its way around these positions, it will of course get smaller all the way to this position, and its phase will initially increase to a crescent phase, but it never achieves a quarter phase or a gibbous or a full phase. Once it turns this corner, the phase starts decreasing back to new because it's again between the Sun and the Earth. So you go from large and new to smaller and crescent to smaller and new, and then back through that pattern to the beginning. And we've plotted this in this figure down here. On the x-axis, we have angular size, the angular diameter of Venus, and on the y-axis, we have the phase. It may be difficult to see, but in this plot, phase runs from 0 to 0.5, where 0.5 would be a quarter of Venus. So beginning at this position here, Venus has a large angular diameter, but a phase of 0, a new Venus. Then as it works its way around, it moves up to this position with a slightly larger phase and a smaller size. Then as it continues, it works its way to position 3 in this figure with its smallest size and no phase. Then it works its way back, number 4 and number 5. Now this is a region because you have some flexibility in the geocentric model. You can make the epicycle smaller or larger within certain limits. So you have a range of possibilities for phase, angular diameter combinations. Now here we have the heliocentric model, much simpler, Sun at the center, and Venus and Earth are both planets orbiting the Sun. So here we have the collection of phases and sizes that we would see from Earth for all the different possible positions of Venus with respect to Earth and the Sun. Here we have Venus at closest approach, so when it's largest, the largest angular diameter it will have, and its phase is new. Then as it works its way around, it of course gets smaller because it's getting farther away from us, and its phase increases to a crescent, but then it keeps increasing. Quarter Venus, a gibbous Venus, then a full Venus because it's going around the back of the Sun. Then it comes back and it gets larger and the phase decreases back to where it began. So here's this plot again. We have the geocentric region down here in blue, but in the heliocentric model, again starting at this position, you have a large angular diameter and no phase, and you work your way up to smaller sizes and larger phases until it's full at this point here. And then you work your way back. So in part C of this lab, you will be measuring the phase of Venus and the angular diameter of Venus for various points in its orbit, and you're going to see where those measurements fall on this plot. They fall in the blue region. We live in a geocentric universe. They fall on this red curve. We live in a heliocentric universe. And here we have a couple links animating Venus as it moves about its orbit in the geocentric model and in the heliocentric model. So you can see how the phases vary and how the angular diameters vary and how they vary in concert. Okay, let's move on to the second background section. So here we're jumping forward in time from Galileo to Kepler and to Newton. So by the time we get to Kepler, he realized that the orbits are not circular, but they're elliptical. The central body, in this case the Sun, at one of the two foci. Focus is singular, foci is plural. Now in this diagram, you can see how to make your very own ellipse at home. It's pretty straightforward. You get a piece of string, tack down both ends of the string, leaving some slack, and using a pen or a pencil, pull the string taut, and keeping it taut, draw the shape that you will draw, and that shape will be an ellipse. Now, some terminology. The long distance across the ellipse, we call that the major axis. And the short distance across the ellipse, perpendicular to it, we call the minor axis. And half the major axis we call the semi-major axis, and that is how we're going to quantify the sizes of orbits. How big is the orbit? We give that by the semi-major axis. And that's denoted with the letter A for axis. Now, the other quantity of importance is how long it takes for the orbiting body to go completely around. And we call this the orbital period, and we denote that with the letter P. And what Kepler was able to show, and this is his third law, is that P squared, the orbital period squared, is proportional to A cubed, the semi-major axis cubed. And what does proportional mean? It means the first thing is equal to a constant times the second thing. So in this case, P squared is equal to some constant times A cubed. And what Kepler found is that constant was the same for everything orbiting the sun, for all the planets. But if you calculated that constant for the moons going around Jupiter, they shared a different constant. And for Earth's moon going around the Earth, yet a different constant. So Kepler realized that the constant depended somehow on the central body, but he didn't know how. And it wasn't until Newton came along and was able to derive Kepler's laws from first principles that he was able to figure out what this constant of proportionality is. And we see it right here. As long as the central mass dominates, like the mass of the sun is much more than the mass of the planets, the mass of planets tend to be much higher than the mass of their moons. So as long as the central mass dominates, that constant of proportionality is 4 pi squared over gm, where g is Newton's gravitational constant and m is the mass of the central body. Now in this lab, you're going to measure the orbital period and the semi-major axis for a moon going around one of the gas giants. So given Newton's form of Kepler's third law, you can then solve for mass and calculate the mass of that central body. Now there are two ways that you could do this calculation. The first way is called plug and chug, and is what you're used to. You take the semi-major axis in whatever unit you measure it in, convert that to, let's say, meters, so it's in the MKS system, and then you would take the orbital period, convert that from whatever unit it's measured in into seconds, so it's in the MKS system. You'd enter the MKS value of g, the gravitational constant, you'd enter pi, etc., and you'd solve for mass, and it would come out in kilograms, after which you'll want to convert it into, let's say, Earth masses. So that's a lot of work, a lot of conversions, lots of possibilities for error. So instead, we're going to try this other approach called the ratio approach. So ratio calculations are far simpler, but they do require some setup and some wrapping your mind around the concept. With ratio calculations, you have a general case and you have a comparison case. For us, the general case is given by this equation, Kepler's third. It applies to anything orbiting anything. In our lab, we'll consider a moon orbiting a gas giant. Our comparison case will be the Earth orbiting the sun. And you see that here. We've entered 1 year for the orbital period, 1 AU the astronomical unit, the Sun-Earth distance, for the semi-major axis, and 1 solar mass for the mass of the central body. So this is Kepler's third law applied to our comparison case, the Earth going around the Sun. And this is Kepler's third law applied to anything. So then all you have to do is divide the two equations. You divide this equation into that equation, and the constants cancel out, the g's cancel out, the pi's cancel out, and you're left with this. Orbital period, measured in years squared, is equal to 1 solar mass divided by the mass of the central body times the semi-major axis measured in astronomical units cubed. In solving for mass, we get mass is equal to a cubed over p squared. It's that simple. If we can get the semi-major axis of this moon going around its gas giant in astronomical units, and its orbital period in years, then we just cube the one number, divide by the square of the other, and we get the mass of the central body in solar masses. Okay, that's it for this background overview video.